Alright, so in this video, we're going to talk about thermometry. Now, there are some things we need to talk about first. There are some minor terms we need to discuss or describe. So, the first is a calorimeter or calorimetry. Now, calorimetry is just the branch of science that deals with the measurement of heat. So, when you talk about measurement of heat, you're talking about calorimetry. Now you use a calorimeter to measure heat, you understand? Heat is sometimes measured in calories. Calories. Yeah, it's a unit of measuring heat. Now we have to define what a calorie stands for. Now a calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree centigrade. Go again. A calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree centigrade. The heat required to raise the temperature of 1 gram of water by 1 degree centigrade. That is the definition of the unit calorie. Sorry, just calorie, not calories, just calorie. If they ask you what is a calorie, that's the definition. Now, another unit of heat, the SI unit of heat is joules. Joules. Obviously, heat is an energy, so it's measured in joules. We have to define what a joule is. What is a joule? A joule is equal to the work done. A joule is equal to the work done when the point of application of a force, when the point of application of a force of 1 Newton is displayed through 1 meter in the direction of the force. Go over it again. It is equal to the work done when the point of application of force of 1 Newton, the point of application of force of 1 Newton is displayed through 1 meter in the direction of force. Now there's a relationship between calorie and joule. One calorie is equal to 4.184 joules. That's it. Now another unit for measuring heat is the British thermal unit, BTU. British thermal unit. This is a unit for measuring heat. Now we have to also define this. This is defined as the quantity of heat required to raise the temperature of 1 pound. These are your right pound, MB, LB. To raise the temperature of 1 pound of water from 63 degree Fahrenheit to 64 degree Fahrenheit. Is related to calorie in some kind of way, because calorie is defined as the heat required to raise the temperature of 1 gram of water by 1 degree centigrade. But when we talk about British thermal unit, it is the temperature required to raise. It is the heat required to raise the temperature of 1 pound. This is pound, POUND, pound of water from 63 degree Fahrenheit to 64 degree Fahrenheit. Now there's a relationship also between British thermal unit and calorie. So 1 British thermal unit gives us 252 calories. Understand? This is basically just the intro. Then we go over to the next phase, which is talk about specific heat capacity. Specific heat capacity. Now, before we talk about specific heat capacity, we need to talk about heat capacity. Now, what's the difference between the two? They have very similar definitions, but the difference is just when we talk about unit mass. I told you guys that unit or unity stands for what? Unity stands for one. So when you hear unit mass, you're talking about just one, just a mass, you understand? So when we hear the word unit mass, you should associate unit mass with specific. So this is just the same thing, but this one deals with specific. Like this one deals with unit mass, while this one just deals with the general mass, you understand? So let's go straight to the definition of specific heat capacity. Now, specific heat capacity is the quantity of heat required to raise the temperature of a unit mass. As I said, it is the quantity of heat required to raise a unit mass of a substance, through 1 degree centigrade. It is the quantity of heat required to raise a unit mass of a substance through 1 degree centigrade. So please note it down. Then we'll talk about some things. Now, specific heat capacity is denoted with small letter C. Yeah, small letter C. So specific heat capacity can be related to some other things, like to some other quantities, like quantity of heat, temperature, and mass. You understand? So the relation is Q, which means the quantity of heat is equal to mass times the specific heat capacity times change in theta. Now this change in temperature, you understand? This can be mc theta 2, okay, mc theta 2 minus theta 1. So this is the relationship between quantity of heat and mass, specific heat capacity, and temperature. Now we are going to discuss the determinations, or the way we can determine the specific heat capacity of various substance. So the determination of specific heat capacity. So there are basically two ways by which we can determine, or we're going to just discuss two ways. And the first way is the method of mixing. And the second way is the electrical method. So these are the two ways we're going to discuss in this video of how we can get the specific heat capacity of a substance. So without talking about much, let's just go straight to it. So we have method. There's an E, method of mixing. So now for method of mixing, there is a general formula we usually use. It's just like if you have, let's say, a substance, an iron bar, and you drop the iron bar. Let's say you have a calorimeter. A calorimeter can just be a copper container, you understand? Let's say a copper container that contains water. And then you drop the hot, let's say, iron rod into that water. What will happen? You first of all, you hear like a sizzling sound. Then if you leave it for like some time, you find out that the metal, that's the small metal rod or the metal stuff, has lost heat. You understand? The temperature will reduce a little bit. Then you also observe that the water will also increase in temperature. You understand? So there's a loss of heat from the metal, and there's a gain of that heat from the water. You understand? This is the metal rod. Let's say you have this metal, you have this container. Let's say this is a calorimeter. It's made of copper. Then inside the calorimeter you have water. So when you drop this stuff inside this water, let's say this is hot, this thing is very hot, and this water is just cold. So when you drop it inside this place, you see that, you observe that there's going to be an exchange of heat between this hot substance and this cold water. After some time, you observe that, let's say this was like 100 degrees, let's say 80 degrees Celsius. This water was like 20 degrees Celsius. After some time, after putting this into this place, you observe that this thing will no longer be 80, rather it will reduce. It can reduce to like 50. This one will also increase, you understand? This one, let's say initially it was like 10 degrees Celsius. It's also increased. So at the end of the day, you have an equilibrium temperature. When you put two of them together, you have an equilibrium temperature. That temperature is the temperature that both this metal, whatever, and the water, when they have the same temperature, that's called the equilibrium temperature. Let's say initially this was 80 degrees Celsius, and this is cold, which is 10 degrees Celsius. And let's say after the exchange of heat, we have 40 degrees Celsius for the both of them. So this is the equilibrium temperature. So we're going to study how we're going to make use of this. Now, first things first, we need to consider two things. We have a solid, which we consider as the metal rod. We have the solid, we have water, and we have a calorimeter. So we also have to consider that. Now, whatever is happening to the calorimeter, whatever is happening to the water, will also be happening to the container, because the container will also gain heat, you understand? So back to this. So we're going to try to draft out a formula for this. So for this kind of scenario, we're going to have obviously the water will lose, the solid will lose heat. So we have heat lost by solid, obviously it's going to lose heat, is equal to the heat gained by water. Now, it's not only water that gain heat, or the calorimeter also gained heat. That's the container. Obviously, when you put that kind of thing and you fill the container, will be warm. So the calorimeter also gained heat. So heat gained by the calorimeter. So this is basically just the idea you're going to use in calculating this stuff. So it's still going to be something like this. It's going to be MC change in theta is equal to MC change in theta plus MC change in theta. Now, the only difference is that when you come to the change in theta, that's where you have a little bit of difference. The M will stand for the mass of the solid. The C will stand for the specific heat capacity of this solid. The M here will stand for the mass of the water. The C here will stand for the specific heat capacity of the water. M here stands for the mass of the calorimeter. C stands for the specific heat capacity of the calorimeter. Now, the difference here is that, remember I said something that when you mix something, we put this solid inside this container that contains water. After you place it inside, I told you that they'll have an equilibrium temperature. Let's say theta E. Understand? Equilibrium temperature. This is the temperature of the hot, right? This is the temperature of the cold, right? So they'll have, after everything, they'll have the equilibrium temperature. So the change in theta you're going to use here is going to be theta hot minus the equilibrium temperature. You understand? For this solid, because it lost heat, you understand? But for these two, the one you're going to use is going to, for the change in theta, you're going to use the equilibrium temperature minus theta cold. This thing, same thing, you're going to use equilibrium temperature minus theta cold, because they gained. That's the only difference, you understand? When you get to where you have to substitute for this change in theta, for this one, it's going to be theta hot minus equilibrium. This is equilibrium minus theta code, equilibrium minus theta code. Do you understand? Now, both the water and the calorimeter will have the same temperature. Don't worry, we're going to solve a question and you see what I'm talking about. All right, let's tackle this question. Now, it said a 30 gram of aluminium piece. So we have aluminium, right? Aluminium is our solid. So let's say the mass of aluminium is 30 gram. Is heated to 100 degrees Celsius. Theta hot is what? 100 degree Celsius. Now you have to convert this to Kelvin. So converting this to Kelvin, you have to add 273. So this gives you 373 Kelvin. Now, what else was given to us? It said, and then transfer to a 150 gram of water. So we have water. We have the mass of water to be 150 gram. 150 gram. At a temperature of 20 degrees Celsius. So this is the temperature of the cold water, 20 degrees Celsius. Adding 273, you're going to have adding 273 to this, you're going to have 293 Kelvin. And they said the final temperature of water was 25 degrees Celsius. That's the equilibrium temperature after mixing the two. Equilibrium temperature is 25 degrees Celsius, which translates to 273 plus 25. This gives you 298 Kelvin. And then I say determine the specific heat capacity of the aluminium. Now they didn't mention anything about calorimeter. Okay, they said in a 64 gram copper calorimeter. Yes, so the calorimeter has a mass. The mass of the calorimeter is 64 gram. And I said something earlier. I said that both the water and the calorimeter will share the same temperature. You understand? So this is 293 Kelvin. So if you can successfully bring out your parameters in this format, you'll be able to tackle the question. So using our previously stated formula, M mass of the aluminium, specific, okay, the question says that take the specific heat capacity of water, CW, to be 4.2 times 10 to the power of 3. This gives you 4,200 joule per kilogram Kelvin. They said take that of copper. Yeah, the calorimeter. I told you the calorimeter is made of copper. So the specific heat capacity of the calorimeter is going to be 400 joule per kilogram Kelvin. Yeah. So they're asking us to find the specific heat capacity of the aluminium. So MC, this is C of the aluminium. Change in theta. Remember, we said the first change in theta is going to be the theta hot minus the theta of the equilibrium temperature is equal to M mass of water, specific heat capacity of water. Then we said the change in theta here will be the equilibrium temperature minus the cold temperature plus the mass of the calorimeter, specific heat capacity of the calorimeter, the same thing, equilibrium minus the cold. Do you understand? This is what will give you your solution. Now, the mass of the aluminum is 30 times this. You're looking for Ca. This is 373 minus 298. This gives you the mass of water is 150 multiplying 4,200 multiplying we have 298 minus the code is 293 plus the mass of the calorimeter is 64 multiplying the specific heat capacity of the calorimeter is 400 multiplying same thing 298 minus 293. So when you do that, you have 30 multiplying the specific heat capacity of aluminium multiplying I think it will multiply 75, giving you same thing 150 multiplying 4,200 multiplying I think this will give you 5 plus 64 multiplying 400 multiplying 5. So let's check. Okay, 298 minus 293 gives you 5. Then 273 minus 298 gives you 75. Yes, exactly. So multiplying this, you multiply the numbers. 30 times 75 gives you 2250 times the specific capacity of aluminium, giving you, when you do all this, you have 3,278,000. Yeah, when you multiply this, sum it up. So in order to get CA, you divide both side by 2250. Divide both side by 2250. So your CA gives you 1456.89. Now the unit is joule per kilogram Kelvin. You understand? That's why we have to convert. That's why we converted our degrees Celsius to centigrade. You understand? Now we go over to the second method. We talked about the first method, which is the method of mixing. And we're going to discuss the second method, which is the electrical method. So we're going to talk about this. Now, electrical method just deals with talking about like trying to heat up something. He's making use of a heater actually. So heat water, I understand. Most of you know what a boiling ring is, something like that. So we're going to go straight to it now. Before we proceed, we know that heat is an energy, right? Heat is an energy. So energy is equal to power times time. You understand? Now, power in relation to electricity is equal to the current times the volt. I stands for current, V stands for volt. So substituting this in, you have Q is equal to IVT. This is one formula. And we also know that power is also equal to current square times resistance. So you can make this capital I if you choose to. So if you impute this thing again into this, you have Q is equal to I square R times time. This is another formula for Q. Thirdly, we know that power is equal to the voltage square over resistance. Plugging it into this equation, you have Q gives you V square T over R. So these are equations for Q. Now we are going to, for the purpose of this video, we're going to just talk about equation 1. But if you see any question relating to equation 2 and 3, it will be easy for you to tackle. So let's quickly erase this. So since Q is equal to IVT, and we also know that Q is equal to MC change in theta, it's safe to say that IVT is equal to MC change in theta. Understand? So let's tackle a question on this. Now, the question says a 3 kilogram iron block. So the mass you understand? This time I'm not working with calorimeter and co. It's just 3 kilogram. Iron block is heated electrically by a 200 watts coil. Now the unit for power is watts, so our power is 200 watts. For 6 minutes, time is 6 minutes, so we have to convert this to seconds. So 6 times 60 gives us 360 seconds. The temperature of the iron block is increased from, so the first temperature is 30 degrees Celsius. Convert this, you add 273, you have 303 Kelvin, and